Good evening. Thank you for choosing Channel 11 News. I'm Isabel in Paris.
I'm Abby Jowett.
I'm Emma Downing. And we have a great story for you today.
It is a great one, Isabel.
Indeed it is.
And who would have thought it all came from a carrot?
Without our topic today, viewers at home would still be watching on a box TV.
That's right, folks. Today we're talking about LCDs.
An LCD is a liquid crystal display. It's essentially a display of information on a screen, which uses liquid crystals that become visible once electricity passes through them. You may have heard of CRTs, but LCDs are very different.
That's right, Abby. Instead of firing electrons at a glass screen, an LCD has a backlight that provides light to individual pixels arranged in a rectangular grid.
So cool. You know what? Let's find out how these LCDs were discovered. And let's break it down to see how it all began with the discovery of the liquid crystal.
We all know the states of matter, liquid, solid, and gas. But have you ever heard of mixing states of matter?
I sure hadn't, Isabel. I know solids, which hold their shape and often have packed atoms in a neat, regular arrangement called a crystal or crystalline lattice. I know liquids, which lack the order of solids, and though they stay put if you keep them in a container and flow relatively easy when you pour them out, and I know gases have no fixed shape or volume and expand freely to fill containers. But I didn't know they could be combined.
That's right, Emma. Liquid crystals are like how they sound. They are almost like a hybrid between liquids and solids. Liquid crystals exhibit some of the order of a solid, but some of the fluidity of a liquid.
So neat. I bet viewers at home are wondering how these liquid crystals were discovered.
I bet so. Actually, Austrian botanist Friedrich Renitzer determined the liquid crystal had different melting points. Let's take a look.
The great Austrian botanist Friedrich Renitzer found such a discovery in 1888. Believe it or not, Friedrich was studying certain derivatives of cholesterol extracted from carrots at the time. Friedrich discovered it had two melting points, 294 degrees Fahrenheit, 145 degrees Celsius. It melted and turned into a cloudy fluid, and at 353 degrees Fahrenheit, 179 degrees Celsius, changed into a clear liquid. He discovered that the liquid crystals reflected polarized light and could also rotate the polarization direction of light, useful in LCDs in the future.
Whoa, Friedrich the Great, am I right?
So right. There was also a man named Otto Lehmann, or let's say Otto Lemon. Let's take a look. Studied the cloudy fluid under a microscope, he saw crystallites. Noted that the cloudy phase flowed like a liquid, but that there were other characteristics, such as a rod-like molecular structure that was somewhat ordered, which convinced him that the substance was a solid. Lehmann continued to study cholesterol, benzoate, and other related materials, and through this he concluded the cloudy liquid fluid represented a newly discovered phase of matter, and it was called the liquid crystal.
Now that we know what liquid crystals are, we can look at the two most important phases of liquid crystals, nematic and smectic.
First of all, the nematic phase. This is where liquid crystals are a bit like a liquid. Their molecules can move around and shuffle past one another, but they all point in roughly the same direction, almost like a matchbox.
So cool. Actually, a nematic liquid crystal causes the polarization of light waves to change as the waves pass through it, the extent of which depends upon the intensity of the electric field.
Yes, that's right. In the 1960s, chemist Richard Williams began to research the use of liquid crystals while he worked for RCA Laboratories. Richard discovered that they were applying a strong electrical field to a thin layer of nematic liquid crystals. The crystals would form stripe patterns. The discovery was called Williams' domain.
Okay,
That's right. Once liquid crystals have cooled, they shift over to the smectic phase. This is where molecules form into layers that can slide past one another relatively easy, but don't move into other layers.
right on, Emma. It's a bit like people working for different companies on a particular floors of an office, because everyone moves around on their floor, but they don't switch between the floors. These have a generally cloudy appearance, which means that they scatter light in much the same way as colloids.
Exactly, Isabel. Once it was discovered that they needed the liquid crystals in the nematic state, They soon realized that they needed to be heated so hot that it was impractical for consumer use. Williams' colleague, George H. Heimeyer, led a team of 2 additional research chemists at RCA, Joel E. Goldmacher and Joseph A. Castellano. And they discovered that altering the number of carbon atoms allowed for the presence of pneumatic liquid crystals at room temperature.
Yes, and in 1967, they produced the first liquid crystal display. Let's check out the clip of this reported event.
Coming to you live outside of RCA Studios, the first ever liquid crystal display. People are going bonkers. Hold on to your hats, everyone. It's a rainy one. Back to you at the studio.
Don't forget about the downfall of this 1967 display.
Downfall?
Yes, don't you remember? This then required hundreds of thousands of volts to operate, making it seemingly impossible for viewers like you to watch from home.
So cool! Learning this valuable information led to the first liquid crystal display.
An LCD is a flat panel display commonly used in TVs, computer monitors, or laptops, such as the one you're watching this live on right now.
Like my cell phone, Isabel?
Yes, mobile phones too.
Too funny. LCDs are unlike the previous cathode ray tube monitors as they operate in a significantly different way.
Just like a piece of cake, LCDs have many layers.
This cake is great, by the way.
You know what else is great? Learning about LCDs. Ooh. Ooh.
The first layer is the backlight. In liquid crystal displays, the backlight provides an even light source behind the entire screen.
First, let's take a look at how light works. Light flows like waves in the sea, but instead of water, it's a wave pattern of electrical and magnetic energy vibrating through space. When sunlight streams down from the sky, the light waves are all mixed up and vibrating in every possible direction.
Right. And that light that passes through the liquid crystals in an LCD must be polarized light. This means that the light waves are only traveling in one plane.
Wait, Abby, didn't you just say light waves are vibrating in every possible direction?
Yes, that's right. In order for light to be polarized, we must put a filter in the way, called a polarizer.
There are 2 polarizers used in an LCD, a horizontal and a vertical filter. Polarizers only allow light waves to pass through if they are traveling in the same direction as the filter. So, when both the horizontal and vertical polarizers are placed together, light is not able to pass through them both.
Right, because the horizontal filter blocks every waves but the horizontal ones, and when the horizontal waves pass to get to the vertical filter, they are blocked and no light is passing through.
Okay, back to LCDs. Let's look at the second layer of the LCD, the first filter, which is the horizontal polarizer. This polarizer filters out all of the light waves except the ones traveling horizontally. So after the light from the backlight passes through the filter, only horizontal light waves are left.
Think of it like prison bars, only sideways. The polarizer is a filter that has a grid of lines going horizontally, very close together. So only horizontal light waves can pass through, but all other light waves are blocked.
After the horizontal polarizer is where the liquid crystals come into play. The liquid crystals make up the third layer. The horizontal light waves need to be twisted to flow from horizontally to vertically, so they can pass through the next layer, which is the vertical polarizer. The liquid crystals allow this to happen. When the crystals are in their nematic phase, they can be sandwiched between the 2 polarizers and twist the light waves so it can pass through both.
The liquid crystals allow the light waves to bend and go from horizontal light waves to vertical light waves, allowing the light to pass through from the backlight, through the first filter, through the liquid crystals, and then through the second filter. This allows light to be seen on the screen as the light waves have passed through all the layers of the LCD.
On both sides of the layers of liquid crystal is a transparent electrode. When these electrodes are charged, it creates an electromagnetic field. This electromagnetic field aligns the liquid crystals in such a way that they stop bending the horizontal light waves.
This causes the light waves from the backlight to pass through the horizontal filter and the liquid crystals, but the light gets blocked at the vertical filter because they are no longer twisted from horizontal to vertical. This ultimately causes the screen to be black, as the light does not pass through all these layers.
Okay, I get it. So when the electrodes are not charged, light passes through, and we can see it on the screen. But when they are charged, we see black. But how do we see different colors and different pictures on our screens?
Good question, Abby. We can see different colors in pictures because the display on the screen is made up of individual pixels arranged in a rectangular grid.
Each pixel has a red, green, and blue subpixel that can be turned on or off. When no voltage is running through all of the pixel's subpixels, it appears black. When the voltage is running through the subpixels at 100%, it appears white.
Right, so the thousands of pixels are individually addressed by a voltage, which determines the color light we see from each.
The monitor adjusts each amount of electricity that runs through each liquid crystal, which runs through each pixel one by one and row by row. This happens about 60 times per second. Crazy, right?
Between that second vertical filter and the protective glass or plastic on the screen is the red, green, and blue color filter over the subpixels.
By charging the electrodes, we can determine the amount of each color that appears on each pixel. The more voltage applied, the more of the color is visible.
What is interesting is the fact that by adjusting the individual levels of red, green, and blue light, millions of color combinations are possible.
Right, each color has a value from 0 to 255, and depending on the amount of voltage applied, the number can increase. So in reality, there are about 256 to the third different possible color combinations.
Let's dive into how light travels through LCDs. Have a look.
If you were to look at an LCD up close, this is how it would look. LCDs are made up of multiple different layers. The first layer is the backlight, which provides a light source for the entire screen. The backlight produces light waves that travel through the polarizers. The backlight produces light waves traveling in many different directions, but because the first polarizer is a horizontal polarizer, only horizontal light waves can pass through, and all other light waves are blocked. If the liquid crystals were not present in the LCDs, the horizontal light waves would be able to pass through the first polarizer, but would get blocked by the second. This is because the second polarizer has been rotated 90 degrees from the first. The liquid crystals will, in their nematic state, have unique properties which allow them to bend and twist the light from horizontal to vertical, allowing the light waves to pass through both filters. After passing through the liquid crystals, the horizontal waves are now traveling vertically and are able to pass through the vertical polarizer. The light waves are able to pass through the second polarizer and hit the color filter. Depending on the color and the amount of voltage applied to the electrodes around the liquid crystal determines the intensity of the color that we see on the screen. If no voltage is applied to the liquid crystal, it is able to twist and bend the light waves. But if a voltage is applied, the liquid crystal remains untwisted and no light waves are passing through the second filter. The light waves are able to be passed from the backlight through the first horizontal polarizer, be twisted, and pass through the second vertical polarizer because of the liquid crystals.
So cool! While viewers at home just learned about different colors that liquid crystals can produce, let's look at the different types of LCDs.
When looking at light sources, there are 3 different types of LCDs.
That's right. The first type of LCD is reflective. Reflective LCDs use ambient light to reflect ambient light into the layers of filters and liquid crystal.
Like a calculator.
Exactly.
The second type of LCD is transmissive, which is a light source, such as LED lights, that direct at a diffuser that creates a uniform lighting pattern over the surface of the LCD. The light from the backlight then passes through the LCD layers.
Like my cell phone?
Yes!
Right on. Thirdly, there are the transflective LCDs as well, which use a special polymer sheet between the backlight and the LCD. That sheet mentioned before is known as the transflector. A transflector allows light to pass through and reflect it.
Like some smartwatches.
Yep, smartwatches where energy saving is their top priority.
I hope you all enjoyed this segment on Channel 11 News.
Next time you watch television, be thankful you don't have to watch on an old box TV.
Know that LCDs made a huge impact on technology today.
This is Channel 11 News. Thanks for tuning in. I'm Abby Jowett.
I'm Isabel in Paris.
And I'm Emma Downing.
Good night.